Welcome all to the next edition of GOAT Seminar. And today we have Alexandra Clifton presenting rainbow separating path systems. Yes.
Right, thank you. So this is all work with these lovely people that I worked with at the Center for Mathematical Modeling in Santiago de Chile. And before I talk about rainbow separating path systems, I'll just give you the gist of why separation might be an interesting thing to talk about. So suppose you have some machine and it has some buttons on it, and you can press the buttons in various combinations to make things happen. And one of the buttons doesn't work, and you would like to know which button doesn't work. So one way to do this is to try all of the buttons, and oh, one of them doesn't work. But maybe it's faster to try various combinations, and you can isolate which button doesn't work by knowing that this was the only button that was in these particular things that didn't work and not in any of the ones that did work. So the idea that each button would have some unique signature of the sets that it's included in. So for here, our buttons are going to be our edges, and the sets that they're included in are going to be paths. So we'll begin with this notion of weak separation. Later on, you will see a notion of strong separation. They're very similar, but they're both going to be important as tools for our third notion of separation, which is going to be rainbow separation. So here we say that a weak separating path system is a collection of paths where for every pair of edges, there's some way to distinguish them, meaning there's some path that includes one but not the other. So for instance, if I'm trying to separate this path of length 4, that's my original graph, I can use this path, and now you see that they all have their unique signature, right? This is only in this one path, this is in both, this is only in the second path, and this is in none of them. So the lower bound that you get from this is going to be log base 2 of the number of edges, because if I have p paths, I only can have 2 to the p different signatures. And upper bound is going to be number of edges minus 1, right? I could just give each of these edges their own one edge path, and then the last one doesn't even need one. That would automatically be distinguished. If I know that I'm in none of the first few paths, then I have to be the edge that's in none of them. And then our other notion of separation is strong separation. So I think both of these groups, when they came up with their definitions, they both just called them separation, but so it goes. So here, as you might expect, it's in fact stronger than weak separation. So for each pair of edges, it needs to be separated 2 different ways. So I need something that has E but not F, and I need something else that has F but not E. So the basic observation here is that if I'm strongly separated, I'm of course still weakly separated. So weak will serve as a lower bound for strong. And worst case scenario is that every edge needs its own path. And in fact, I believe for this, that's exactly what we're going to need. So we can see that from this, the weak separator that I gave you as an example is clearly not a strong separator, because for a strong separator, for every pair of edges, I need something that has this one and doesn't have this one. Well, nothing at all has this one, so that clearly fails. And it turns out that when I have a path on n edges, I'm actually going to need the full n. And the reason for that is because how do you separate this edge from this one? The only way to do it is to have a path that uses this but not this, which must be a singleton path. Well then, how do you separate this one from this one? I need some other path that is either this or this, and then by induction, you see that every time I have a new edge, I need a new path. So the 4 that I've given you here is the best that you're going to get. Okay, so the authors of the weak paper conjectured that for a general graph with n vertices, there would be able to be a separating system that was linear in the number of vertices. And most of the attention that ended up going into this afterwards was on finding upper bounds for strong, but of course an upper bound for strong gives us an upper bound for weak. So what do we know about strong? So the authors that introduced the notion of strong path separation showed this n log n upper bound, and then Letzter came along and improved it pretty close to the conjecture by getting this n log star of n. And then just maybe a year and a half, 2 years ago at this point, this group came along and they actually resolved the conjecture. They showed that for any graph on n vertices, there is a strong path separating system with at most 19 n paths. So we've seen here that you definitely need linear, and they showed that the answer really is linear. This 19 is probably, I don't think anyone really believes that this is best optimal. This is kind of a relic of the proof. I think the best we can hope for would be 2. I'm not sure exactly how much people are pushing on trying to improve the constant in that problem. There's some more interesting questions, perhaps. There's people working on trying to do this for cliques, where we know for weak the upper bound is, I think, n+1, and for strong, n+9. There's people that are extending this to using things other than paths. So there's been some work on that. But I want to talk about kind of a different notion of covering altogether, where the paths are colored. So I could, I guess, explain where I got this idea from, but it's kind of off topic. So you can ask me later if you want to know, but otherwise I'll just say we have our collection of paths. There are some that are red, there are some that are blue, and when we separate a pair of edges, we do it in such a way that there's either a red one that has this, but not that, and a blue one that has this, but not that, or the other way around. So for every pair, I'm going to give you 2 paths of different colors that distinguish them both ways. So it's like strong, except with this other colored restriction. And you can see in my picture here, for instance, the 2 edges on top of the C4, how are they separated? Well, this one has the red one that doesn't use that edge, and then this one has the blue one that doesn't use that edge. And you can check that, yes, in fact, all 10 pairs are separated by this picture. What's maybe harder to check is that this construction with 6 is actually best possible for this example graph. So how is my notion of coloring separation related to what we've already talked about with weak and strong? So first basic bound that we can observe is if you take your red and blue separating thing and you get rid of the colors, well, I still have something that includes E but not F, something that includes F but not E. It's still strong. So I'll say that C2 is the minimum size of this red-blue separating system, and C2 is bounded below by the size of strong. The other important observation is that if I just look at the red ones, they form a weak separating system. And if I just look at the blue ones, they also form a weak separating system. So C2 is bounded below by twice the size of weak. And then as far as upper bounds, what we can do is we can get weak plus strong in the following manner. So let's suppose I have a weak separating system and I paint the entire thing red. So for every pair of edges, I can pick one of them to be E, one of them to be F, so that I have a red path that has E but not F. Now, I would like to have a blue path that has F but not E. Well, maybe I wasn't careful about, for this pair, I labeled this one as F, but for that pair, it ended up being F. But this one, something was F with one pair, but E with another pair. So in order to be super careful, I'll just say for every pair, I'll get a blue one that separates both ways. So the point is, if you have a red weak and a blue strong, you can combine them in order to get my red-blue separator. So any questions before I talk about our results? Is everybody clear on the definitions? Yeah.
So you will continue thinking only about 2 colors.
I will continue thinking about 2 colors for 80% of the talk, and then I will add more colors.
Okay.
Okay. So I will warn you, though, that one thing I have not really justified is that this C2 is an interesting parameter at all. Maybe it's some silly combination of weak and strong in some way. So part of what I want to show with these first few results is that C2 is actually worth studying. It's not just some silly function determined by weak and strong. It's actually something new. So for paths, we were able to find the values exactly. So essentially, it's the number of vertices plus 1, or the number of edges plus 2, with the exception of some small cases that happen to behave a little bit better. And if I'm trying to justify that C2 is worth studying, then maybe I haven't done the best job just by talking about paths. So the two bounds I want you to remember, that C2 is bounded below by strong, and that C2 is bounded below by 2 times weak. So for strong, we talked about if I have n vertices for a path, the answer is n minus 1. Okay, eventually the answer is n plus 1. So this bound is not tight, but okay, it's asymptotically tight. If the answer is always something like strong plus 2, big deal. For weak, I haven't talked really about what weak is for a path, but it's essentially n over 2. So to give you a sense of why that's the case, it's a path I've drawn with 8 edges. And now I'll make a bunch of paths that are about half the length. And you can see that this is in fact a weak separator. And we can also check that it's the best possible. So essentially for a path, weak is about n over 2. Sorry, this is a 2. I mean, it's true, but it's not interesting without the 2. So weak is about n over 2 for a path. Strong is about n. So that's saying both of the basic lower bounds from before would give us about n, and I told you the answer is about n. So haven't really done a good job justifying that you might care about C2 independently of weak and strong. Okay, well, what about cycles? So for cycles, we claim the answer is 2 times ceiling of n over 2. Real quick, I think I can essentially justify where that lower bound would come from. So look at 3 consecutive vertices along your cycle. I need some path that has this one, but not that one. I need some path that has, I need some path that has this one, but not that one. And I need some path that has this one, but not that one. So essentially each vertex is going to be an endpoint at least twice. And that actually justifies that the answer for strong is at least n. But of course I can take each edge individually. So the answer for strong literally is equal to n. The answer for weak, you can essentially get n over 2 by just folding this picture in on itself. So if I add an edge over here, it doesn't stop me from using all these long paths that I've already given you. So for weak, again, n over 2 times 2 would give a lower bound of n. And for strong, we get a lower bound of n. And the answer I gave you, okay, sometimes it's n plus 1. But again, if I'm trying to justify that C2 is not essentially asymptotically predetermined by knowing strong and weak, again, cycles are not helping us. Okay, let's try to find some other way of justifying that C2 isn't simply determined by strong and weak. And here I will give you stars. So here's my star. And essentially, where does this bound come from? Well, if I have 3 edges in my star, I will give you the following 4 paths. So I will give you a red path and a blue path that cover these 2 edges. And I'll give you a red path that covers these 2. And I'll give you a blue path that covers these 2. So there's only 3 pairs of edges to check. I will check at least one of the pairs. So how do I separate these 2 from each other? What I can do is I can use this blue one that only covers that, and I can use this red one that only covers that. And you can check that all the pairs work. So here we're able to separate a 3-edged star using 4 paths. But generally speaking, we can separate, I'm not going to worry about the floor or whatever, but asymptotically, you can separate a star that has n minus 1 edges, n edges, whatever, using roughly 4n over 3. And the reason you can do that is you can just pick off 3 edges at a time and use this over and over and over again. So you might think, well, okay, you're using 4 for 3, you do this over and over again, you get a ratio of 4/3. But what if we were clever and we decided to handle 4 edges at a time? Because here, I'm going to give you a star with 4 edges, and I can actually separate it with just 4 paths. So indeed, like take these 2, for instance, I can use that red one and that blue one. Or I take these 2, for instance, I can use that red one and that blue one. So as far as looking at comparing a star with 3 to a star with 4, the star with 4 is more efficient, right? Because you covered you dealt with more edges, and you have the exact same number of paths. But asymptotically, we do not get n, we get 4n over 3. And that's because this one does not scale in the same way that this one does. So here, because every edge was contained in both a red path and a blue path, if I pick off 3 edges over here, and then I pick off 3 edges over there, and I keep going, these are going to be compatible with each other. The problem with this is I cannot spam using this over and over again, because if I have my all red edge from the first 4, and I have my all red edge from another 4, then there's no way to separate them. So it turns out that you actually get 4n over 3, and the lower bound here is actually quite easy to check if you use the existing results, because the weak answer is about 2n over 3. In fact, I think in this case, C2 is exactly equal to 2 times weak. Strong is, of course, not going to be any more than the number of edges. So the fact that we got 4n over 3 when the number of edges is n is the first instance I've shown you where this is asymptotically different than strong. But it's not asymptotically different from 2 times weak. So again, we are not able to demonstrate that this is any different than 2 times weak. Okay, finally, I will give you an example where it is different than 2 times weak. So instead of looking at stars, why don't we take all these branches and extend them by 1? So we look at a spider where all the legs are of length 2. And here, we were able to actually figure it out for any number of legs, figure it out exactly, and there's some silly cases that are different. But the thing I want you to really focus on is that here, just like when the legs were length 1, the answer is again roughly 4n over 3. But in this case, weak is actually going to be better than what we were seeing before, because there's this result here that says if you have a tree, with the exception of one tree that is not this, so it's fine, if you add up the total number of degree 1 and degree 2 vertices, then half of that is going to serve as an upper bound for strong, and of course as an upper bound for weak. So for a spider, all but one vertex is degree 1 or degree 2. So this upper bound that you get would be ceiling of, I guess, n minus 1 over 2. So the lower bound then that you get from 2 times weak is not going to be any more than n, but here we've given you an example of C2 being about 4n over 3. So finally, we've justified that C2 is something that you might want to study that doesn't trivially follow from knowing what's going on with weak and strong. And now that we have that, I guess we can say that retroactively our other results are now interesting again. But also, our main result is to show this upper bound for trees. So we're able to show that for a tree with n vertices, or maybe I prefer to talk about things in terms of edges. So a tree with e edges, we get an upper bound of 4e over 3 plus 2. I firmly believe that we can get rid of this plus 2, but I'm trying very hard not to tell any lies, so I will include it just to be careful. It'll become clear later why that's persisting there. So I want to talk about our proof for trees, but in order to do that, I'm going to have to talk about paths anyway. So I might as well talk about the proofs for paths first. So I guess I will start by drawing a path. And I will draw a path with 6 edges because this is kind of the smallest case where the answer is n plus 1. So if we can justify that this is n plus 1, we'll understand why everything bigger is n plus 1. And as for smaller stuff, well, there's just a finite number of cases. You can just do them by hand. So why is the answer n plus 1 for sufficiently large paths? Well, the thing to note, and this is true for any graph where you have a degree 1 vertex adjacent to a degree 2 vertex, you need to separate this edge from this edge. So I need some path that has this edge but not this edge. There is only one way to do that. Take a path that has literally one edge. Well, if you do that, I'll do it on this side so I don't have to keep reaching over. So if I have a path that's literally this edge, good for me. I've potentially separated this from some other stuff. What I have not done is I have not separated any of these edges from each other. So I'm still going to need at least C2 of Pn minus 1 in addition to that edge. So if I can show that you need 8 to handle P7, then you need at least 9 to handle P8, etc. So why do you actually need 8 paths to handle P7? So we'll pretend that we can do it with 7, and we will show that that does not work. So what I want to do is I want to focus your attention on the paths that are length 1. So obviously we need a path of length 1 here. Maybe it's blue, maybe it's red. I need a path of length 1 here. I might have some paths of length 1 somewhere else, but let me just pretend that I have one here. The point is, if I have some blue paths and I ignore them, I'm still going to need a red weak. I'm still going to need a blue weak separator on the remaining edges, because these paths are not doing anything at all to separate these 4 edges from each other. So if these were my only blue paths of length 1, I have 4 more edges that they are not separating from each other. And we said at the beginning that a simple lower bound on the size of a weak separator is log base 2 of the number of edges. So if I have 2 blue paths of length 1, then I'm going to need at least 2 more blue paths to separate the remaining edges. So what I can do is for each edge, for each path of length 1, I'll keep track of that. So let's say I have blue, I have B blue paths of length 1, I have R red paths of length 1. There's some subtlety here where if I have a blue and a red on the same edge, I'm actually just going to ignore one of them, but it's not a big deal. And then I need to have a weak separator on the edges that are not affected at all by these blue ones. And I need a red weak separator on the edges that are not affected at all by these red ones. So the size of that blue weak separator is going to be at least log base 2 of, in this case, 6 minus b, the number of remaining edges. And then for the red weak separator, I'm going to need at least log base 2 of 6 minus r. So just to give you a silly example, if I have 2 blues of length 1, then I'm going to need at least 2 more blues. Let's say I have 1 red of length 1, I'm going to need at least 3 more reds. And that means I'm going to need at least 8 total, where for the sake of contradiction, we assume the answer is 7. So it turns out most of the cases can just be handled by using this trivial log base 2 bound. The only case that you have to worry about that doesn't immediately follow from this is if, say, b equals 2 and r equals 0. Because if b equals 2 and r equals 0, then all I'm getting from this is that 2, 0, 2, and 3, well, that's 7. That's what I'm aiming for. I will show that it's actually still not possible to get 7, though. Because if you only have 2 paths of length 1, where do they have to go? They have to go in the 2 places that are guaranteed to have paths of length 1, namely here and here. So now, if you want to get 7, then you have to find a weak separator for the remaining 4 edges that only uses 2. And you also need to find a red weak separator for the whole thing that only uses 3. So I've actually given you a weak separator for a path with 4 edges at the very beginning. It looked like this. And up to symmetry, that is the only thing you can do. Now, that was for separating these in the middle. That says nothing at all about what's happening on the outer edges. So potentially this path could be extended like that, but we'll find out that it doesn't matter one way or the other. This one cannot be extended though, because the point is for this weak separator to only use 2 paths to separate 4 edges, there has to be some edge that's not covered by any of the paths. So if I want any hope of getting 7, the blues have to look like this. Now, what do I do about the reds? So this is not covered by any blue paths. So it needs to have some red path that includes it and doesn't include this edge. And it needs to have some red path that includes it and doesn't include this edge. So let me just check my notes so I don't make a mistake. Okay, so I need something that includes this one, but not include this one. So time to get a new marker.
Don't place these markers.
Okay, so I have this, and potentially I extend it as well. Now, that may have helped me separate this from this. It did not help me separate any of these four edges from each other. So I'm still going to need a red weak separator on these four edges over here. And without loss of generality, there's only one way to do it. And even with losing generality, is the guarantee that one of the paths is the one that uses precisely the middle two edges. So then that's what 6 of our 7 paths look like. And then why does this cause problems for us? Well, here I gave you a choice that we either had length 1 or length 2, but really it had to be length 2, because if it was length 1, we would have been done at the beginning. Also, feel free to interrupt me if I'm saying anything that sounds weird. So our first 6 paths, with the exception of this one, you have a little flexibility, have to look like this. And now the problem is every path so far that includes this edge includes this one. So I need to add some path that has this but not that. And every path so far that includes this edge includes that one. So I need to have some path that uses this but not that. So I only have one more path that I'm allowed to use, and it needs to use this, not use that, use this, and not use that. So that just doesn't make sense. So we've established the lower bound for P7, and that establishes the lower bound for everything. So what about the upper bound? So I'll pivot back to the slides. So for the upper bound, we get to use this path extension trick. So the idea is if I have some construction that works so far, then we'll do 3 things to turn our construction for Pn into a construction for Pn plus 1. We'll take this is kind of what's indicated by the squiggly lines. So you take your path of length 1 at the end and you extend it to a path of length 2. You take your path that ended at Vn minus 1 and had the same color as your path of length 1, and you extend that so that it now goes to Vn, and then you add a new single edge path in the opposite color to deal with the edge Vn plus 1. So we haven't affected any of the relationships between the first n minus 1 vertices. So the only thing we need to check is that the last 2 edges, Vn minus 1 Vn and Vn plus 1, are properly separated from everything else. So for Vn minus 1 Vn, so I'll just assume the colors are as they are on my picture for Pn plus 1 here. I have a blue path from Vn minus 1 to Vn plus 1. So I'm going to use that, and then every previous edge before Vn minus 1 is part of some red path that's not using Vn minus 1 Vn. So that's how I get the separator there. Notice I am assuming that every previous edge is part of some red path, but the base construction we get for P7 is such that every edge is in paths of both colors. So that's an additional property that we don't need for the definition, but we need it for this proof to work. But the base construction has it, so it's fine. And now for dealing with the last edge, we can see that we have this singleton path that's red, and then every previous edge is in something blue, and in particular something blue that doesn't use that last edge. So we're able to extend this, and that means that the lower bound is tight. We actually get n plus 1. Okay, so now that we have that out of the way, I want to talk about trees. So I'm going to draw you a tree. And the way that we're going to deal with trees is we're going to eat them piece by piece. So we have this notion of a bear spider. So think of this as being a bear spider. And the idea is, if I could find a properly sized separator for my bare spider, I will use all those paths, and then I will remove this, and then I will find a bare spider in the remaining graph, find all the paths I need to separate that, or I'll remove that, and I'll keep going. And the only thing I need to do is make sure that the pieces that I'm removing, the paths that I'm adding, are not so big. So if I remove E edges, I don't want to use more than 4E over 3 paths. And I also want to make sure that I'm doing this in such a way that the paths I use to handle these will be enough to separate these edges from those that remain in the graph that are handled later. So the formal definition of a bare spider, it's a subtree that's isomorphic to a spider. We have some head vertex of maximum degree that only has one edge outside of the spider. The remaining graph is connected, so it's still a tree. The leaves are down here, so something like this is a spider, but it's not a bare spider. We need to go all the way. And we also want everything except the leaves and the head is degree 2 in the spider. It should also be degree 2 in the original graph. So if I had this part hanging off over here, now this would no longer be a bare spider because of this vertex here. Instead, I would use this as my bare spider. So the point is, there's always going to be some bare spider that we can pick. And how do we deal with the bare spiders? Well, some of them are easier to deal with than others. So here's something that you've seen before, and it's very easy to deal with, right? If you have a bare spider that's a 3-edged star, you can deal with it with 4 paths. And the thing I want to point out is with these 4 paths, every edge is covered by paths of both colors, which will be helpful later. For 3 legs of length 2, here you can do it with 8 paths. Again, that's 4/3 times the number of edges. And the nice thing about this is on each of those legs, let's pretend I add another edge here, then I can do the same path extension trick that I showed for paths. So I could add an additional edge, so I have a new path of length 1 that's blue. I would extend this red one, and I'd extend that red one. So we'd always be able to do n+1, and in particular, that would be at most 4/3 times the number of edges, and each edge is covered by paths of both colors. So I've marked these as relevant spiders. How are they relevant? Well, some bare spiders are easy. So to summarize, if you have 3 legs of length 1, you can deal with them. If you have 3 legs of length more than 1, you can deal with them. And if you have 2 legs that have a total of at least 6 edges, then we can use our path construction to handle those, and you can deal with that. So when I say deal with, you're not necessarily dealing with the whole bare spider. I mean, if the whole bare spider is one of the graphs I described, okay, great, you killed the whole spider. But what we can do is we maybe break off pieces of the spider. So for instance, if this was my bare spider, it had 4 legs, and then these 3 legs, let's say, were all length at least 2, then I can deal with this piece, and now I've reduced it to just being that. So you can reduce your spiders as you can, but at some point you might get stuck. And what are the potential places you get stuck? Well, you're going to have at most 2 legs of length 1 left, and you're going to have at most 2 longer legs that are left. And your 2 longest legs are going to have a total length at most 5. So any contradiction to what I just said is the stuff that was handled in the previous slide. So there's this not particularly nice looking, but also not super intimidating list of possible leg lengths to worry about. So if you have 1 leg of length 5, or your 4 legs of length 3, 2, 1, and 1, these are some cases that you still need to consider. And some of them aren't so bad. So if you only have 1 leg left, so let's suppose I have this bare spider here and I've managed to kill all of that except for this piece here. Well, then you don't need to think of this as a bare spider anymore. Just think of it as part of the leg of the next bare spider. So anytime that you only have 1 leg, you can defer it until later by just combining it with what will ultimately be the next spider. Some of the cases, there's actually just some construction where you can do it with at most 4/3 the number of edges anyway. So we can ignore those. And then there's stuff like 3, 2. So this is 3 and 2. where if you want to do it with 4/3 the number of edges, you need to do it with 6, and you can't do it with 6, or at least you can't do it with 6 in the way I want to do it, which is that I want every edge to have the additional property that it's colored by paths of both colors. But unless it's the entire graph, we have something else we can use. We can use the one additional edge that's incident to the head. So instead of this being a 3 and a 2, it's a 3 and a 2 and this extra edge that I'll call the hat. And that 3, 2, 1 graph, that actually can be done using at most 4/3 the new number of edges. So some of the things that you couldn't deal with immediately, you can deal with now that you have the hat. So there's only 4 cases. So here there's maybe like 17. There's actually only 4 cases that are bad, which we call bad spiders. There's 3, 1, 2, 1, 2, 2, and 2, 1, 1. The good thing is if you have 2 bad spiders, then they're not so bad anymore. So if you have a 3 and a 1 over here and a 2, 2 over there, they're different parts of my tree. There's some path connecting the heads of the spiders. And you can find, thank you to Ana for making these great pictures. You can find a separating system for the combination. And this part in the middle is just saying that there is this blue path that's using intervening edges. But here, I'm actually taking advantage of the hats as well. So including the hats, I have 10 edges. I actually give you 13 paths, which beats 4/3, such that every edge in one of these bear spiders is not only separated from the others within the same bear spider, but it's also separated from the ones in the other bad bear spider. The only problem is when we do this, how do we make sure that the edges that we're removing, because after we add these, say, 13 paths to our collection, we're going to say, remove these edges, and keep going. How do we make sure that the edges we removed are actually going to ultimately be separated from, in particular, the intervening edges that need to be handled later? And the key to that is that each of these edges, even the ones that are using a path that includes intervening edges, also are using paths that are not leaving their particular bear spider. So let's suppose there's some edges here in the middle that are being covered by this blue one. So later on, when they get handled as part of another bear spider, they're going to get a new red path and a new blue path that covers that edge. And this one had some path that didn't cover that edge. So we can use this one and the one that's coming later to separate the edge from this bear spider and the intervening edge. So this is really why I keep insisting on every edge being colored by paths of both colors, even though that's not part of the definition. Because if you imagine that, let's say later on, I have some edge and I separate it and I only cover it with blue stuff. Well, if something earlier was only covered with blue stuff, or maybe was also covered with some blue stuff and one red one, but the red one used these intervening edges, namely this one, that would cause a problem. But if the edges that I'm removing as part of the bad spider have both colors on their paths that are not using the intervening edges, then it's not going to cause any problems separating later. So we're able to keep doing this. And ultimately, okay, if you have 2 bad spiders, you're fine. If you have 1 good spider, you're fine. When do you get stuck? You get stuck if you only have 1 spider and it's bad, or you only have 1 spider and it was good earlier for sort of wishy-washy reasons. Namely, we said a path was good, but a path was good because we could defer it to later. If it's literally the last thing, you can't defer it any longer. And then there's also the cases where they were good because you could use the hat. If that thing was literally the entire graph, there's no more hat to use. So you have to worry about that as well. But at this point, there's only a finite number of cases, none of which are particularly large, and we can check all of them. And it turns out that they all have separators of size no more than 4/3 the number of edges. But here, as I said, I don't want to lie. I'll say 4/3 plus 2 because I'll add 2 dummy paths that don't actually help with the separation, but they help to make sure that there's no edge that's only covered by red stuff and no edge that's only covered by blue stuff, so that it doesn't mess up the compatibility with the previous stuff. Yeah. Oh, that was not a hand, that was my time. I see. Okay, so that more or less finishes things up for trees with 2 colors. Then I'll actually use the name of the talk, which is we define rainbow separating path systems for more than 2 colors. And the idea is just that for every pair E and F, there's going to be some path that has E and not F, some path that has F and not E, that are distinct colors from each other. And more colors just makes your life easier. So if we define CK to be the smallest size of this, CK is at most CK minus 1. This lower bound is actually the exact same thing that we saw before for getting the lower bound of 2 times weak. The idea is pick your favorite color. If you use all the paths that are not that color, that forms a weak separator. So essentially, you do this K times because everybody has a different favorite color. You get K minus 1 different, you get K different weak separators, and each thing is used K minus 1 times. And for 3 colors, I will not explain where this result came from, but we're able to show that for a certain type of spider, we need 17/16 times the number of edges. In practice, we don't know an upper bound better than 5/4. The 5/4 comes from the same sort of bad spider, bear spider breakdown, just that when you have 3 colors, it's easier to get a lower ratio, so there's less to worry about. So we end up getting 5/4 instead of 4/3. And really the reason that I care that this was 17/16 is because if you have more than 3 colors, you can actually just do it in N. So the point was that 3 colors is kind of this intermediate zone where, okay, it's an improvement over 2 colors, but it's this last case where you don't have enough colors to just do it in N. And of course, if you can do it with N for 4 colors, you can do it with N for more colors. And there's always going to be paths where essentially we pick off the edges one at a time like we saw before, and each one is going to need a new path if we're trying to get N, so you can't do better than N. So I will introduce some new notation at the end, which is essentially just saying ignore lower order terms. So we have the CK for a graph class, and if you consider bigger and bigger graphs in this graph class, what's like the worst case scenario in terms of the ratio of CK of the graph divided by the number of vertices? Well, if we have the class of all graphs, we know that there's this result that strong is at most 19n. So of course, weak is at most 19n. So 2 times weak is at most, so strong plus weak is at most 38n. So actually these values will always exist. They're always at most 38. To summarize our results for paths and cycles, we see that C2 of P and C is 1. To summarize what I just told you about trees, we see this 4/3, the unknown C3, and then 1 for C4 or for any C5, C6, etc. This I don't think I'll have time to talk about, but for actually, I'll go for it. So for complete graphs, we're able to show this lower bound of 3/2, which is essentially saying 3n/2, and I don't care about lower order terms. So how does this happen? So the key is to show that virtually every edge of your Kn needs to be included in at least 3 paths. And the reason for that is hardly anything is going to be in only 1 path, because the number of paths is at most the strong plus the weak, so it's at most 2n plus 10. So there's going to be a linear number of edges that are in at most 1 path, 1 for each of those linear number of paths. And the key is to focus on the edges that are in exactly 2 paths. So look at this long blue path. How many edges does it cover that are in exactly 2 paths? Well, for each edge that it covers, think about what other path uses that edge. And let's suppose 2 of the edges that it covers, the other path is red. Well, then these 2 can't be separated from each other because the blue one isn't separating anything because they're both part of that path. And the red ones are not separating anything because they're the same color. So that means the blue one, the number of edges with only 2 paths covering it that it covers is at most the number of colors, so it's at most k. So the size of the set E2 is just going to be at most k times n. So I have a linear number of edges that are covered less than 3 times. So I have n squared over 2 edges that are covered at least 3 times, and the longest path length is n minus 1. So to cover all of these, I'm going to need at least 3n over 2. And then the last thing that we care about is we can consider the limit of these CKs, because the limit does exist. And the question is, for a sufficiently large number of colors, do you actually hit the limit, or is there going to be some graph class where you're getting closer and closer but never getting there? All right, thank you.
Any questions?
Yeah.
So for most of the proofs, you somehow use that you will have a part of each color covering the edge. If you add this requirement to the definition, does it change a lot?
It really wouldn't change a lot. So for instance, the one thing I didn't talk about, so this C3, it's 17/16 n minus 1 minus 3. How the minus 3 came about is there's at most 3 since there's 3 colors, there's at most 3 edges that are only going to be in paths of 1 color. So the very first thing I did in that proof is I said you have at most 3 edges, so you can add at most 3 in order to have a separator where everything is in paths of multiple colors, and then did the whole proof with this condition anyway. So, I mean, yeah, if you make this new definition, it'll never change the answer by more than k. And given that the stuff that we're dealing with is linear in the number of vertices, k is a negligible constant. So, yeah, I mean, you could definitely use this alternative definition, and it wouldn't really change anything. Except that we do kind of like the cases where we can get the exact constant. In particular with the trees, if we could get rid of the +2 would be nice, because I don't think it really needs to be there, and it somehow looks better without it.
Any other questions?
Yeah.
So here you consider the path system. So but if you consider something more general, like let's say, I don't know, let's not be brave too much, maybe trees. So what if instead I was covering the ground with trees and not paths? What would change? Or is anything about?
So for this graph, I think if you're covering with trees, then well, I don't know actually. So I mean, I guess my first answer is that I don't have a good answer. I mean, obviously you can make it smaller because you have more flexibility. There's results on paths and cycles. I think one of the kind of interrelated notions I haven't really talked about is this notion of, okay, don't care about separating, we care about covering. Like, what's the fewest number of paths or fewest number of paths and cycles that you need to cover all the edges? There's stuff about that. Some of my co-authors plus other people in Chile have some other separating thing, but off the top of my head, I don't remember what object they were using to separate. I think there are some silly things that you need to do where you need to, for instance, if I want to separate with cycles, I can't literally separate everything with cycles, because what if you have an edge that's not in any cycles? Or what if you have a pair of edges where they're in literally the exact same cycles? So to get around some issue like that, they might say something like separate with cycles and single edges. So there are some caveats where you might need to add something extra like that. I mean, of course, if we're talking about trees, we can just talk about trees, but I don't have any insight as to what would happen.
So what's okay? So you mainly considered paths, cycles, and trees, which make total sense if you're covering with paths. But did you also consider any other classes which are less path-like, let's say?
I guess not really, because oh, okay, I mean, okay, sorry. I mean, yes, we consider complete graphs, but other than this, I would say not really, because I guess generally complete graphs in and of themselves. Notice that this is kind of like the asymptotics for more colors. Complete graphs for 2 colors we didn't actually consider because the basic bounds we get that I talked about at the very beginning already get you between like 2n plus 2 and 2n plus 10. So the thought is maybe any further improvement is just going to come from directly improving stuff for strong and for weak, which is stuff people are actively working on. So yeah, there's this issue of trying to zero in on a class where you can get an interesting result about this rainbow stuff independently of just working on weak and strong. So, for instance, I mean, we didn't try to do anything at all for rainbow on the class of all graphs because the thought is you're getting some basic bound using this 19n. The 19n is probably not close to tight anyway, so the improvement probably just comes from pushing at the original weak or strong. But yeah, there may be some good candidates for stuff that we just didn't consider.
Anything for addition?
We didn't make any progress for random graphs with our rainbow stuff. There are results for random graphs with the original definitions, but we didn't go in that direction.
Okay, let's thank the speaker again.